Section 35.9 Temperature dependence of rate constants. The Arrhenius equation is an empirical formula for the temperature dependence of the reaction rate constant. So let's look at this formula. K is equal to A times e to the power of E sub A over RT. K is the rate constant. A is the pre-exponential factor in the Arrhenius equation. E sub A is the activation energy or energy barrier. R is the gas constant. T is the reaction temperature. Now let's analyze this reaction rate constant. Imagine you have two reactants, A and B, about to react with each other. The reaction rate is proportional to the collisional frequency between our A and B. And also it's proportional to the percentage of the collisions with the right collisional orientation. Let me explain this. Imagine a reaction between a hydrogen radical and water. Let's say the product is H2 and a hydroxyl radical. So the hydrogen radical takes away one hydrogen atom from the water molecule. If you are looking at this example, the hydrogen radical must attack one of the two hydrogen atoms in water. If the hydrogen radical attacks the oxygen atom, no reaction will occur in this case. So now let's get back to this Arrhenius equation. This A, again, is proportional to the collisional frequency and also to the percentage of the collisions with the right collisional angle. What about the exponential function? This exponential function tells us the percentage or the probability of the collisions that have enough energy to overcome the reaction barrier. Now let's look at a graph here. Okay, so this part you have energy versus the fraction of molecules with specific translational energy. At 200K, you have more molecules with lower energy. At 500K, you have more molecules with higher energy. And now let's say reactants collide with each other, but they also have to overcome this activation energy or reaction barrier this much. Now if you look at the 200K situation, only a very small percentage of the reactants have enough energy. So this much under the blue curve, this much can overcome this energy barrier. Now let's look at this 500K situation. Now you have a much larger area here under this red curve, but above this activation energy, so you have a larger percentage of the reactants with enough energy to overcome the barrier. So again, three conditions. They have to collide with each other, and two, the collisional angle must be right, and three, the colliding parties must have enough energy, and then a reaction will occur. So now you may wonder, isn't this collisional frequency dependent on temperature as well? Yes, it is. So there's a modified Arrhenius equation. Now if you look at the modified Arrhenius equation, you can see over here this A is replaced with lowercase a times T to the power of m. So this part takes the temperature dependence of collisional frequency into account. And also this part takes the collisional orientation into account. It can also be interpreted as the entropic effect. You will see that later. By using this formula, it's slightly different from the original Arrhenius equation. Again, in the Arrhenius equation, this part is simply uppercase A, the pre-exponential factor. But now we have two terms. This lowercase a times this temperature to the power of m. M can be just any real number. So this is slightly different with one more parameter m, and usually this is more accurate than the original Arrhenius equation.